way, way, way long ago, okay, with a guy called Democritus, okay? Democritus had the first kind of ideas about atoms, and he said that all matter is divisible, which means it can be broken up into smaller parts. All right, he said that until the basic unit was reached, you could break it down. But once the basic unit, right, what he called the basic unit reached, you couldn't do it anymore. And he called that basic unit the atom, okay? The atom, the word atom means indivisible. Now, what do we know about the atom today? Can we break it up into smaller parts? Yeah. Yes. What are the three smaller parts of an atom?
Protons, electrons, neutrons.
Very good. Protons, neutrons, and electrons. So what he said was on the right track, right? Atoms are the smallest part of an element, but they have particular properties and characteristics about them that make them that type of element. All right. But the problem was no one believed him. Everyone believed Aristotle. Okay, Aristotle came in about 300 BC, and he just said that there is basically matter could not be broken down. He said that matter was a type of a whole, right? And he really had 5 elements. Okay, have you heard Aristotle's 5 elements? Right, fire, water, something, something, something. I don't know, air, whatever. Those 5 elements. Yeah, it's something. I don't know what they are. Okay, but he said there's only 5. And that everything is basically made up of those things, right? People believed him for a long time, okay? A long time, until we started making modern scientific discoveries. When we say modern, we mean within the last 100, 200 years, right? So it's still really, really relatively recent. Okay, so now let's move into a little bit more modern. In the late 1700s, people had already kind of decided, or I'm not going to say discovered, they'd already kind of laid the foundation for what an element was, right? They had some identifying characteristics of what made an element. At this point, they had an idea that chemical reactions happened, right? That if you put 2 things together, something new might come out, right? That's a big indicator of a chemical reaction, or an important part of a chemical reaction is that something new is formed. And so they had an idea about that stuff. This information they had, although it was rudimentary, led to the most kind of basic fundamental chemistry law that we have, which is the law of conservation of mass, which says mass cannot be created or destroyed, right? Mass cannot be created or destroyed. When a chemical reaction happens, mass does not get created and does not get destroyed. It just changes forms. The atoms themselves rearrange, right? They move around and they bond with different things. That's what happens in a chemical reaction, okay? Once they had kind of determined or kind of laid out this law of conservation of mass, that we can't create or destroy matter, it led to what's called the law of definite proportions. And the law of definite proportions says that once a chemical compound is established and a ratio of those elements is established, that compound will stay the same, right? Regardless of how many of those, how big the sample is that we take of that compound or whatever it is, right? We know that water is, do you know the chemical formula for water? H2O. So we know water has a ratio of 2 hydrogens to 1 oxygen. And so what that means is that any sample of pure water we take would have the ratio of 2 hydrogens to 1 oxygen, right? No matter where we get that sample from, whether we're looking at 1 water molecule or 1,000 water molecules, right? They're going to all have that same ratio. So basically, once a compound is determined and its chemical characteristics are determined, that compound stays the same ratio. Okay? All right. Scientists also had an idea that elements don't just combine in one way to form one compound, right? Hydrogen and oxygen come together to form water, but they also form other things. What is H2O2? Do you know what compound that is? H2O2? No, it's hydrogen peroxide. Hydrogen peroxide. So do you know what, have you used hydrogen peroxide before? Right, to clean something? So very close to water, but also very not close to water, right? It would be a big problem for us if we drank that by mistake, okay? Because although it seems very similar, 1 more oxygen, it can't make that big of a difference, right? Well, it does, okay? So this discovery or this thought that they can combine in multiple ways leads to what's called the law of multiple proportions, okay? The example I gave up here was with carbon and oxygen. It combines to form all sorts of different things, but carbon dioxide and carbon monoxide are a good example as well. Okay, so the law of multiple proportions says chemical compounds are formed by whole atoms chemically combining in different ratios. Why do you think it's important that it says whole atoms? Right? If we know that the ratio of hydrogen to water is 2 to 1, can't we just have HO 1/2? Isn't the ratio the same there? Right, isn't it double the amount of hydrogens to oxygen? The ratio is the same, but can I have half of an oxygen atom? No, right? Because if I take half of oxygen's material away, right? If I take 4 of its 8 protons away, it's no longer oxygen, right? I can't have half of an oxygen atom. It's not oxygen anymore. If I have half of an oxygen atom, it's now beryllium, right? Because if I take away 4 protons and I'm left with 4 protons, that means I'm left with an element beryllium. Okay? So we can't have half of an atom. So we can't do all of the ratios, and when we make chemical compounds have to be whole numbers. When we build chemical compounds like this, do you know what this is called right here? A subscript, okay? And this subscript applies to what element? It applies to the H, okay? So here it's telling us there are 2 hydrogen atoms, and then if there's not a subscript listed, what do we assume is there? A 1, right? We don't write it, but we assume there's a 1 there, okay? So that'll come up for us a little bit more in later chapters again, but if there's not a subscript listed, H2O, we assume that there's 1 oxygen and 2 hydrogens, okay? So let's start talking about what we know today in atomic theory, okay? What do we know today about the atom? We know today that all matter is composed of atoms. All matter is composed of atoms, and atoms are different types of elements, right? There's lots of different things that we can make with all of our elements. Atoms, we know that atoms of one element differ from atoms of another element. So what that means is that all of our elements don't behave the same. Hydrogen does not behave the same as sulfur. Sulfur does not behave the same as calcium, right? Different elements have different properties. They have different chemical and physical properties, and so they behave differently. So this is what I consider today's definition of the atom. Okay, and I think I have it in your notes for you. You don't have to write it out. I would highlight a couple things in here that I want you to look at. In today's definition of the atom, it says the smallest particle and element that retains the chemical properties of that element. Okay, so the atom, it's not just the smallest part of an element. It has to have the chemical properties of that element to still be considered an atom. So we can't just consider a single proton or a single electron or a single neutron. That's not an atom, right? An atom has to have a certain arrangement of protons, neutrons, and electrons to be considered an atom, right? So an oxygen atom has to have 8 protons, has to have a certain number of neutrons and electrons.
What's a quark?
Okay. We're going to talk about a guy named J.J. Thompson. He did an experiment and basically experimented with metals and found out whatever metal he was working with, these metals all were giving off a negative charge, right? They all had this negatively charged area around them. And so he put together a lot of different things and a lot of different theories, but his main discovery was that he called this negatively charged stuff, right? These negative charges, electrons. So J.J. Thompson is responsible for the discovery of the electron, okay? He kind of came to the conclusion if these are in all metals, then they must be in all elements. And so he was able to apply his theory and his knowledge into the whole, everything we knew about elements at the time. So he discovered the electrons. Okay, after he was kind of done, other people did experiments about the mass of an electron. And it says the mass of an electron is 9 times 10 to the negative 31st of a kilogram. Okay, so really, really, really like infinitesimally small, right? It is really insignificant in terms of mass, and we'll see that a little bit later with our proton mass. Other things that were gathered from Thomson's theory about electrons is that since our atoms are mostly neutral, and he knows that we've got negative charges in that atom, right? He knows we've got electrons, yet somehow our substance is coming out neutral. There has to be something that's offsetting those negative charges, and those have to be protons, right? He called them protons. Because what's the charge of a proton?
Neutral.
No. What's the charge of a proton? It's positive. A proton has a positive charge. So he had to figure out that because our atoms are mostly neutral, there's got to be something that's balancing that. Then he also said, since electrons have very little mass, or very insignificant mass, there's got to be another particle that's accounting for, or that's having an effect on the mass of an atom. And so what's the other subatomic particle that affects only the mass, not the charge? A neutron, right? Very good. All right, so here is Thompson's model of the atom. Okay, it's called the Thompson model, and it's also called the plum pudding model. Plum pudding model, okay? And it's called that just because it looks like just a bunch of stuff floating around, right? There's just, the electrons are just floating around. It has an overall positive charge, but the electrons are evenly dispersed throughout the atom. That was his thought on the atom, was that it was evenly dispersed. Protons and electrons were evenly dispersed throughout the atom. Okay, so the guy that came next, Ernest Rutherford, he made a different discovery. Okay, Rutherford did something called the gold foil experiment. Have you heard of the gold foil experiment? Oh, you do? Okay, old pros. Okay, the gold foil experiment means Rutherford took these things called alpha particles. And alpha particles are heavy particles with a positive charge. That's what's important here. They are positively charged. So I want you to be thinking about that as we're talking about the gold foil experiment. So you had a thin gold sheet, and he shot these positively charged particles through this gold foil. Okay, his expectation was that they were going to pass right through, right? Knowing what they knew at that time, which was Thompson's model, all the elements just were an even spread of positive and negative. So his positive particles were just going to go right through. It wasn't going to be a big deal. But what actually happened, right, here's kind of the expectation. Based on the Thompson model, his expectation was that his positively charged particles, if they hit something else, would just pass through. But here's actually what happened. Most of them did pass through the gold foil, but some of them were redirected or deflected the minute they hit that gold foil, right? Something caused them to veer off their path. So if you've got a positively charged thing going straight, what would cause it to be deflected? It would have to be a positive charge, right? Because positive and negative would attract, right? And positive would repel, right? Think about ends of the magnet that don't go together. You know what I'm talking about? You have two ends of the magnet that aren't supposed to go together, and they just repel. They won't stick, right? That's what's happening here. So a positively charged something was running into it, okay? His conclusion is that there's got to be a region in an atom that is small, and it's really positively charged. Okay, so he said there's a dense, positively charged region at the center of the atom, and he called it the nucleus. Okay, he said if my alpha particles are being redirected, okay. He called it the nucleus. His suggestion was that electrons would then orbit that nucleus. Okay, he said there's a region in the middle that has a positive charge, and then the electrons would orbit similar to a planet orbiting the sun. And so his model, the Rutherford model, is also called the planetary model. Okay? What he said was that in these orbits, that means most of the atom is really made up of empty space. And I'm going to show you his model here in just a second. Okay? His is also called the planetary model, but I want to show a little bit of the gold foil experiment. Okay? So they went right through. A lot of them did. But some of them that we think hit the nucleus ended up being redirected, okay? And so if you visualize on these orbits a single electron, let's say there's an electron right here, and let's say there's an electron over here on this orbit, and let's say there's an electron right here on this orbit, that would then mean that all the rest of the atom is empty space, right? The lines wouldn't be there. Right, that's just showing us where they would orbit to and from. Okay, so look how much of that is empty space. Right, a lot. And so it allows other particles to pass through that. Today, we know differently about how electrons fit around the nucleus of an atom, but this was what we believed for a little bit, right? Rutherford's model is kind of an important step forward in atomic theory. And we'll get into what we know about electrons a little bit more in chapter 4. All right, today we know that the nucleus is made up of two kinds of particles. Do you know what's found in the nucleus? Has to be protons, and what's the other one? Neutrons. Okay, protons and neutrons are found in the nucleus, and they make up all the mass of the atom. Okay, protons have a positive charge, and they have a mass of 1 AMU. Okay, AMU stands for atomic mass unit. An AMU has somewhere around 10 to the negative 27th of a kilogram. So we're still about 1,000 times larger than an electron. Okay, because electrons were negative 31st. And so it's still a really, really tiny unit, okay? But neutrons have no charge and also a mass of 1 AMU. So protons and neutrons have equal mass. They contribute to the mass equally. Protons and neutrons are held together in the nucleus because it doesn't seem like a positive and a neutral should stay together, should they? What should attract? Positive and negative, right? But positive and neutral are allowed to stay together in the nucleus by something called nuclear forces. And those are they're kind of a study all on their own about how they actually stay together, but they're called nuclear forces.